Welcome to Electrons Classroom series. I'm Daniel Krishi. You guys know different sources of electrical energy like solar, thermal, wind, nuclear, and more. But today I would like you guys to see electrical energy generation from the most fundamental perspective. That is to get to know the underlying basic principles and effects behind them. If we were to condense these principles in the order of prominence and practicality, we'll get 5 such principles originating from rotating magnetic fields, light, heat, chemical reactions, and mechanical vibrations and pressure. So maybe get a cup of coffee and enjoy the video. Okay, so the first principle of electrical energy generation, we have rotating magnetic field, which is essentially, electromagnetic induction. So what electromagnetic induction is basically, by Michael Faraday, is whenever you have a conductor, and mostly we have a coil, and nearby the coil, if you have a magnetic field that is generated by a magnet. In this case, we have a permanent magnet. It can also be an electromagnet itself. And we have these magnetic field lines starting from the North Pole and terminating at the South Pole. So according to this effect, whenever there is any change in magnetic field that is experienced by this coil, we will have an EMF induced across the coil. And this EMF is nothing but the voltage, in open circuit condition, basically. So how can we change this magnetic field, right? There are different ways using which we can do that. Most simplest method can be just the linear motion. You can just swivel this magnet back and forth, and what will happen is that the intensity that is experienced by this coil will change as the distance between the magnet and the coil changes. And the other way you can change the magnetic field is simply by rotating the magnet itself, right? And this is usually what happens in electrical generators, right? We have a rotating magnetic field that we use to generate the EMF or electrical energy, because it is very easy to have rotational, like continuous rotational motion, as compared to just this linear vibratory motion, which is ultimately driven by the shaft of the generator, where you provide the mechanical input through, say, a turbine. Mathematically, we can quantify this EMF that is induced in the coil, and it goes something like this. EMF is equal to negative of the number of turns of coil and the rate of change of magnetic flux. So what this equation tells us basically is that the EMF that is induced in the coil is in the opposite direction to that of the motion or that flux. So what it does, whenever you have this EMF induced, and when you connect a load across the coil, the current that flows as a result of this EMF and the load connected, this current actually produces its own internal magnetic field, right? So you'll see its own internal magnetic field, and this field is actually in opposite direction to that of the external magnetic field, right? So there is a clash between these two, where you really see the physical impedance, right? This is where you need to burn real energy, whenever you have the generator. If you have nothing connected across the terminals of the electrical generator, you won't see any physical impedance while you turn the shaft. But when you connect the load, because this non-zero current is now flowing and creating its own internal magnetic field, which conflicts with the external magnetic field, and that's why real work has to be done. And the equation for phi, that is our magnetic flux, is B, that is nothing but magnetic field strength, multiplied by A, that is the area of the coil, and the cosine of the angle between the perpendicular of the coil and the external magnetic field. So according to this equation, if you want to have more EMF produced in the coil, it is important that you keep maximum of the magnetic flux as much perpendicular to the coil's plane as possible, so that you'll get more of the EMF. And you can clearly see it from here, because we have cos phi, so phi has to be 0, cos 0, then we'll get this quantity will essentially turn as one. So then you'll get, the maximum flux.
And this method is no doubt the most popular electrical energy generation method in use, as you can convert any motion kind to basically have changing magnetic field and have just a coil placed nearby so that you can tap the EMF. For example, if you would like to tap wind energy, you just have to make really aerodynamic blades that you need for the turbine, and then that can drive the shaft of the generator, and ultimately, you'll have EMF. Same is the case with any other technology like, tidal energy generation, where you have repetitive motion, where you tap the wave energy, convert it again into changing magnetic field.
And on the second number, we have photovoltaic effect. And this method really came into picture when we started exploring the semiconductors. So, in a very similar fashion to how LED works, when you provide some current to it, it glows and illuminates. You can have an effect basically in reverse. So, you have P type semiconductor and an N type, and this is just a simplification. It is much complex than this, but essentially what we have is a PN junction. There is a junction in between them, and this thing is also sensitive to light. So whenever you have, visible light shining into the junction, there will be an open circuit voltage that is generated, and typically it is between zero point 0.5 to zero point 0.7 volts per solar cell, which is the fundamental element of big solar panels. And as we all know that solar in the recent years has been gaining a lot of traction, in a lot of countries which are closer to the equator. We, receive a lot of sunlight. For example, India, then we have Central America and some African nations. They receive good amount of sunlight, which can be then converted into electrical energy. And the key trick here, the construction of the solar cell, is to make the upper layer as transparent as possible, so that the light can shine through from above and actually reach the junction where the real magic happens. This is a very complex topic in itself, and there is an entire research branch which is focusing on increasing the efficiency of solar cells. And also another trick that you can use is have some kind of reflective layer behind the bottom layer, so that some of the light that goes beyond the junction can be reflected back, and some small portion of it can be absorbed. The beauty of this technology is that it is really clean and totally stationary, totally free of any moving parts. So this is not like an electromagnetic generator. This is just simply stationary. You just have to shine light, and then you get energy. So these things are really compact. You can use them as long as you get sunlight. So many of the times we use them in space missions. We deploy them on the space probes to have energy from the sun. Obviously, as your space probe moves away from the sun, the intensity of the light will decrease, but definitely this is at least something that you can use. Now, one very important thing to note here is that please don't be confused between another effect which might seem very similar to you, which is photoelectric effect. So, photoelectric effect is a very different effect, and this was discovered by none other than the really famous Einstein. This effect, if I were to describe it as simply as possible, I would say it is a sensing effect, or something that can be used in sensors but not to generate energy. Okay, so how it works is that you have two metal plates, and you place them either in a vacuum or inside an inert environment. So you can have any kind of inert gas, and you actually apply an electric field, you apply voltage. So whenever this thing gets sunlight, the light of appropriate frequency, which is able to knock off the electrons from the metal plate itself. Sorry about the direction, it should be this one. And this electronic emission really depends on the kind of material you are using. So let's just assume that this terminal will emit the electrons, and then these emitted electrons will follow the electric field that is already present, right, and will actually move to the opposite side. And because we now have flowing electrons, so definitely in the external circuit we'll see, some current flowing, and this current is what we measure. And this is nothing but because you are actually getting current when you have some light. So this thing can essentially be used as a light sensor, and it is known as photocell. So again, you need to remember that this is not a way of generating, electrical energy, and that is really the photovoltaic effect, which needs semiconductors. Here it's just gas filled tube. And to be really honest, these days with the advancement in semiconductor devices, we don't really use this photocell anymore, unless and until it is a very niche application. We mostly use more advanced things, like we have, photodiodes. These are just, you can think of them as really small solar cells, photodiode. So basically just a smaller version of this solar cell. And you can also use, of course, LDRs, that is light dependent resistor, which is quite similar to the photocell, but you just have a material, that actually changes its resistivity when exposed to light. All right, on the number third, we have Seebeck effect. Now, this effect can be realized using different technologies, but at the very basic, what it is, let's say if you have two different metals that you connect together. So this is metal A and this is metal B on the both sides. So here you actually have these two junctions, right? Junction number one, junction number two. So what is observed is that if these two junctions are kept at two different temperatures, non-equal temperatures, you'll actually see some voltage developed across these points. So for example, on this end, you can cool it by keeping it in ice water, and the other one you can heat using a burner. This is just for an example. You will get a voltage generated which can be used to power our loads, though this voltage that is generated is very less, and the current is also not that much, but when you combine this on a bigger scale, definitely you can power things. And this same effect can be achieved using more advanced semiconductor technology. In this case, what they do is you can have N type and P type. Again, this is just a very basic and simple diagram connected. And what you do is you heat one side, let's say this one. So you heat this one and you cool the other side. So this side, and you'll get a voltage. Now, again, as with many of the effects in physics, we see that many of the things are reversible. So here it's the same. We can also generate temperature differential when we provide this voltage externally. So let's say if you apply like 12 volts to this, unit, and by the way, these kind of units, they are known as Peltier units because it derives its name from the Peltier effect, which is essentially just the reverse of the Seebeck effect. So whenever you provide power to this cell, and same is the case with this metal version as well, right? When you provide this voltage externally, you'll see one side of or the first junction absorbing heat, and that means that junction will be cold, as compared to the other junction that will emit heat. And the basic formula for the voltage generated, or vsebec, is given by a coefficient s into delta t. Now delta t is basically the temperature difference between the two sides, right? So delta t is the temperature differential. So S here is the Seebeck coefficient. Basically, this is a property of a material which tells us the sensitivity, and how many volts this thing can, produce per degree change in temperature, right? And this temperature, again in metrics, is Kelvin. So this is volts per Kelvin. Okay, so this effect is really useful in a sense that, again, there are no moving parts here, right? You can directly convert the temperature difference into electricity. So this is really useful in cases where you need a very compact power source. So a very good example of this is the RTGs that are used on the space probes, and also the Martian rovers. So what they are basically is these small thermocouples. And basically a thermocouple is this that I showed you, maybe in this primitive metallic form, or this sophisticated semiconductor form. And multiple of these units are used to build up the voltage and also the current that can be generated. And the heat basically for this device is provided by the nuclear reaction, that is the nuclear fission reaction that we see typically with radioactive materials like plutonium and uranium. But there is a big drawback. One of the drawbacks is that this is not very efficient. I cannot recall the efficiency, but it is very very less as compared to steam turbines and other technology. Because one of the reasons is that you constantly need to maintain this temperature gradient, right? Delta T must be maintained. And you know very well that it is not easy. It is definitely not easy to keep these temperatures. And if you want higher output, you need a very big difference in temperatures, and that is very hard to keep, because ultimately the temperature will travel, right? The heat actually travels, right? There is no way you can totally block it. So with time, what happens is that these temperatures try to equalize, and this is again not helpful. Now coming to the fourth one, that is electrochemical effect. Now, this effect means when we derive our energy directly from the chemicals, right? So there is some kind of chemical reaction going on, and in majority of the cases, it is nothing but a redox reaction. If you guys know from your electrochemistry classes, is that this is nothing but some form of redox reaction. And redox reaction is a combination of oxidation and reduction, right? So red is a short form of reduction, and ox is short form for oxidation. So we'll take the example of very famous example of zinc carbon cell, the typical pencil cell that we use in remotes and other devices. So we have some chemicals filled in, and we whenever we connect some load, right, to the cell, what we see is these two following reactions. So number one, we have on the anode, we see the zinc metal gives up two electrons, and on the other side, on the cathode, what we see is that just reverse of this reaction. Basically, now you will absorb the electron, right? So it looks something like this. We have manganese oxide. By the way, all of these chemicals are already present in the cell. Then we have NH4 plus, which actually comes from the dissociation of ammonium chloride. And then this thing can absorb two electrons, and we have the resulting compounds. And these two reactions basically runs continuously until all of the material inside the cell is used up. So that's why these cells can no longer be used after some time. But there is another version of this that actually can be used indefinitely, and there you actually provide these materials from outside continuously. You are continuously feeding the required reactants into the cell, and these kind of cells are known as fuel cells. And you guys might know a very good example of this is hydrogen fuels, right? Hydrogen fuel cell, which we mostly use for the electric vehicles. And one of the major benefit is that the byproduct of this hydrogen fuel cell is nothing but just water, and that can be easily evaporated or discarded freely in the environment without any kind of problem. and added to the fact that it is very easy to produce hydrogen using electrochemical cells. Whenever you do hydrolysis, you can easily make hydrogen out of water, and that you ultimately use up in the fuel cell, and that creates water. So it is, a complete cycle. And if we come to the math, then if you really would like to go into the depths, the voltage formula, the EMF formula for the cell actually comes from the Nernst equation, but researchers have narrowed down and made standard equations when you do calculations in a standard environment, right? So in that, you simply need two variables. That is, if you would like to calculate the EMF of the cell or the open circuit voltage, that is, the standard potential of cathode minus the standard potential of anode. And according to the standards, the standard potential for the cathode material in this kind of chemistry, the zinc carbon, is plus 0.74, minus the standard potential of anode is negative 0.76. And when you simplify this, it will be 1.5 volts. And these standard voltages used here are nothing but the potential of these materials when you compare it to the standard hydrogen electrode, which is just used for comparison, and which means that it is essentially assigned a potential of 0 volts, basically a reference. Okay, so lastly, on the number fifth, we have piezoelectric effect. Now, this effect is very basic, and it is related to crystalline materials. So, for example, some kind of salts or even glass in the form of quartz. You might have heard about quartz crystal being used in clocks and as oscillators in electronics, or more specifically resonator. So what this effect is, consider we have some crystal sandwiched between two electrodes. Let's say this is our top electrode and this is our bottom electrode, and we connect our voltmeter here. Whenever we strike this crystal, whenever we strike this assembly, or subject it to some kind of mechanical vibration, so this actually results in some voltage developed across these plates, and the reason actually lies deep into the crystal itself. That is, whenever there is a physical stress on this crystal, you actually see a slight shift in the charges, across the cell. So you guys know about the electron cloud, right? So because of this physical stress, you see that these charges, shift a little bit, and due to that, electric dipoles are formed. And whenever there is an electric dipole, definitely you see that you'll effectively have a voltage difference where you place the probes, right? But this voltage is obviously very small because the energy in vibration is not significant, but definitely you can use this as a source of energy when you multiply this, have multiple cells in either series or parallel, similar to what we did in the thermocouple, or the thermoelectric generator. So this piezo voltage that is generated across the crystal is given by the piezoelectric charge constant, that is D, which basically tells us the sensitivity of the material to the applied force, right? How well it responds to certain amount of force, multiplied by T, that is thickness, divided by the permittivity of the material. Permittivity, you guys know that this is how well a material can support electric field inside it, and the area of the surface where you apply the force. So clearly from here you can see that the area is very important, but the other thing that is also considered is the plane in the crystal itself, how you are cutting the crystal, right? This is a little bit more complex, but you guys should know that the plane, how you cut the crystal, is also as important as just the area, because whether you are cutting that against the crystal or in the direction of crystal. And if you are wondering that if reverse of this effect is true, then you're right. And this is where we actually use piezoelectric speakers or piezoelectric buzzers, right? So if you can provide a changing voltage, changing voltage signal to the crystal instead of getting that voltage, so basically like applying an external changing voltage to the crystal, you will see this voltage, this crystal will physically deform. So when you provide the voltage, you will see this crystal physically deform, and that thing will actually generate sound, right? And basically corresponding to the frequency of signal that you're providing, the voltage frequency, you will see equivalent audio signal coming out of, or sound signal coming out of the crystal. And this is an alternative to our common speakers that we use, that are electromagnetic kind, where you have a coil and magnet assembly, and you pass the signal from the coil, and its internal magnetic field's interaction with the magnet will produce sound. But here it is purely on a crystal scale. But the major drawback of using this as a speaker, using piezo speakers, is that its frequency response is typically on the higher side, right? It's not, you typically don't get lower frequency sound reproduction out of piezo speakers. So it's very easy to use as a tweeter, or high frequency buzzer, but you cannot use it as subwoofer or woofer. For that, you definitely have to go with the conventional electromagnetic kind of speaker. Okay, so talking about the practical application of piezoelectric effect. So there is a very novel application where we can use this, is on the roads. So there we see a lot of vibration on the road, right? Especially the internal combustion engine based vehicles, they produce more vibration, right? And that the surface has to absorb. So why not use that vibration to generate electricity, right? And there is also like changing pressure, right, or the weight of the vehicle that keeps moving. So if we can integrate this in our roads, we can produce energy. And as you might imagine, it is very hard to do, but there are some companies, like we have one company in Israel known as Innovatech, and they're working on a project to generate electricity from vehicles running on the road. And for their first prototype, they have already built 1 kilometer of road stretch that is expected to generate 200 to 400 kilowatt hour units, like kilowatt hour, or units per year. Now this is not very much in comparison to what we get from our conventional energy sources, but still, considering that you are essentially tapping energy that would otherwise be wasted. Now, apart from these, there are also few other methods of electrical energy generation, but I feel that they are not that much significant and practical. But I would still like to mention them. We have static generation, and this is basically just the static electricity. When you rub two different materials, like a glass rod and some fur, you get charge separation, and which is governed by the triboelectric series, if you guys would like to know. But as I said, that the energy produced by this is very much insignificant. First the charge builds up. It is similar to that of capacitor, how we charge the capacitor and we discharge it, but it is not significant, right? When you connect these two back, then they can equalize, right? But this transfer is insignificant, except in the case of thunder, or in the case of lightning strike. Lightning definitely carries more energy, but it is very challenging and very dangerous to capture this energy. Regardless of this, extensive research is going on to figure out how can we do this. So in conclusion, every kind of electrical generator that we have uses these fundamental principles, either directly or indirectly, such as nuclear energy generation derives its energy from the radioactive materials like uranium and plutonium, which disintegrates and produces heat, which can then in turn be tapped using RTGs or steam turbines. Well, I hope that you enjoyed the video, and if you did, then please like, share and subscribe. Comment down below if you have any questions, queries or any suggestions. Thanks for watching, and see you there.